September 2025, NASA has placed its monitoring teams on heightened alert after the confirmed detection of 3I Atlas, only the third interstellar object ever identified. Its hyperbolic orbit leaves no doubt that it arrived from beyond the solar system. The shock is not its path alone, but its timing. Astronomers once believed such visitors might be seen only once every several 100,000 years. Yet in just 8 years, 3 have already crossed our skies. The odds are vanishingly small. Is this simply a lucky clustering revealed by better telescopes, or does 3I Atlas hold clues that point toward something far more profound? Perhaps even the key to life beyond Earth? The discovery of 3I Atlas began with a detection made by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, based in Hawaii. On September 2025, the automated survey flagged an object moving at an unusually high velocity and on a trajectory that appeared to be hyperbolic. Within days, the International Astronomical Union's Minor Planet Center confirmed the object's interstellar origin and officially designated it as 3I Atlas, marking it the third known visitor from beyond our solar system. Astronomers immediately drew comparisons to the first 2 confirmed interstellar objects. The first was 1I Oumuamua, discovered in 2017, a cigar or pancake-shaped body that displayed unexpected acceleration not fully explained by gravity alone. The second was 2I Borisov, discovered in 2019, a more conventional comet that exhibited a dust and gas coma, but was still recognized as extrasolar in origin. 3I Atlas is different in several respects. Early estimates suggest it is smaller than Borisov, but brighter than Oumuamua, with an unusual light curve pattern that is still being analyzed. Its speed relative to the Sun exceeds 30 kilometers per second, a clear indicator that it is not gravitationally bound to our system. The trajectory places its origin outside the reach of the Oort cloud, confirming it as a true interstellar object. For astronomers, the excitement was immediate. At the same time, confusion set in as the pace of these discoveries seemed to defy older statistical models, forcing the community to reassess what was once considered an almost impossible event. But was this discovery simply luck, or the start of a pattern? For most of modern astronomy, the arrival of an interstellar object was considered a once-in-many-lifetimes event. Models constructed before 2017 predicted that an object entering from outside the solar system might only be detectable once every several 100,000 years. The sheer vastness of interstellar space and the limited volume swept by planetary systems made such encounters statistically remote. Yet within only 8 years, astronomers have recorded 3 distinct arrivals. In 2017, Oumuamua surprised observers with its elongated shape and unexplained acceleration. In 2019, Borisov entered and behaved like a classic comet, yet carried the signature of interstellar chemistry. Now in 2025, Atlas joins the record, confirming that these events are not isolated curiosities but part of a clustering that few predicted. The odds of 3 confirmed detections in such a short window are vanishingly small under earlier models. Some researchers attribute this apparent clustering to improved detection capabilities. The last decade has seen a dramatic increase in wide-field survey power, with systems such as Pan-STARRS, Atlas, and soon the Vera Rubin Observatory scanning the skies at unprecedented speed and sensitivity. In this mainstream view, the universe has not changed, only our ability to notice it. Others, however, remain unconvinced that observational bias alone accounts for the numbers. A minority of researchers point to the possibility of a deliberate injection pattern, suggesting that these arrivals may not be random debris, but objects arriving on trajectories that are not fully natural. This idea remains speculative and outside consensus, but it persists because the statistics alone invite doubt. The question therefore remains: are these objects cosmic accidents that happen to arrive while humanity's eyes are finally sharp enough to catch them? Or could they be something built rather than born? The orbital path of 3I Atlas already sets it apart from most near-Earth comets and asteroids. Its inclination relative to the plane of the solar system is steep, suggesting an approach from a region not aligned with the majority of planetary orbits. This geometry reinforces the conclusion that it is interstellar, because natural solar system objects tend to cluster in planes set by planetary formation. Projections indicate that Atlas will reach its perihelion, or closest approach to the Sun, in late 2025. As it nears this point, ground-based observatories face a significant observational challenge. For several critical weeks, the object will pass very near the line of sight to the sun, a period known informally as a blackout window. During this time, Earth-based telescopes will be unable to track it reliably because of solar glare, leaving astronomers partially blind. This blackout window has precedent. Both One-Eye Oumuamua and Two-Eye Borisov slipped through similar periods when tracking was lost or severely degraded. For Oumuamua, that gap meant critical questions about its acceleration and shape were left unresolved. For Borisov, certain chemical signatures could not be fully monitored during its closest approach. With Atlas, the stakes feel higher. Instruments like the James Webb Space Telescope and the European Southern Observatory are preparing carefully timed campaigns to capture as much data as possible before and after the loss of visibility. The question lingers: what happens during these invisible windows? And could they conceal behaviors we are not equipped to witness? As observations of 3I Atlas accumulate, the first anomalies are beginning to surface. Photometric sum measurements, which track variations in brightness, reveal an irregular light curve that is not easily explained by a standard rotating comet or asteroid. Rather than a smooth or chaotic flicker, some datasets suggest a repeating pattern that cycles approximately every 11 hours. Researchers have tentatively described this as a thermal heartbeat, a periodic rise and fall in brightness that could indicate reflective surfaces or systematic orientation changes. Patterns in astronomy rarely repeat so neatly by chance, which leaves scientists wondering whether this rhythm is natural or something more. In natural terms, this is puzzling. A typical comet nucleus tumbles in a non-uniform way, producing uneven spikes of brightness as volatile materials sublimate. The cycle of Atlas appears more regimented, less like a random tumble, and more like an object that is turning or adjusting in a controlled rhythm. Several astronomers caution that the data remain preliminary and that photometric noise could be creating the appearance of a pattern. A more speculative hypothesis proposes that the repeating light curve might indicate flat, reflective surfaces such as panels or structured geometries. If that were the case, Atlas would not resemble a natural ice and dust body, but something engineered. This view is far from consensus, but it persists because of parallels to the unexplained acceleration once attributed to Oumuamua. Adding to the intrigue is an unverified claim circulated among amateur forums that an internal NASA memo has categorized Atlas as a candidate for non-gravitational acceleration. If true, it would mean scientists already suspect forces at work beyond simple gravity. For now, the anomaly remains unexplained. The central question is unresolved. Is Atlas a fragment of a comet behaving in a strange but natural way? Or could it be a fragment of something engineered? To place Atlas into context, some astronomers are revisiting past cases of unexplained behavior in smaller bodies. One example is Comet C2020 F8, also known as SWAN. This comet was discovered in early 2020 by the Solar Wind Anisotropies instrument aboard the SOHO spacecraft. As it approached perihelion, observers documented a dramatic tail disconnection event where the comet's ion tail appeared to detach and vanish, only to reform later. Tail disconnections can occur naturally due to interactions with the solar wind and magnetic field lines. Yet the case of SWAN drew unusual attention because of timing and intensity. Amateur radio operators reported coincidental interference in certain frequency bands during the comet's closest solar passage. These claims were never formally investigated, and no peer-reviewed paper confirmed a direct connection, but the reports linger in community archives. Today, some researchers outside the mainstream are re-examining SWAN as part of a possible chain of anomalies that stretch across multiple objects. They argue that the combination of unusual tail events and unexplained electromagnetic interference echoes the irregular signatures seen with both Oumuamua and Atlas. In this interpretation, SWAN may not have been an ordinary comet after all, but part of a recurring pattern of objects that exhibit signatures inconsistent with standard models. This view remains speculative, but the foreshadow is clear. If Atlas follows the same sequence of anomalies, astronomers may be confronting not isolated curiosities, but repeated signatures, each one whispering of a deeper phenomenon. The central question driving the study of interstellar visitors is energy. With Oumuamua, scientists observed a slight but persistent acceleration that could not be fully explained by gravity. Borisov, by contrast, behaved more like a standard comet with sublimation and outgassing providing natural propulsion, although even there some chemical ratios were unusual. Atlas now presents a fresh puzzle, with its early data hinting at deviations that may not align with expected outgassing rates. To accelerate an object the size of Atlas requires significant energy. In natural terms, sublimation of volatile ices can provide thrust, yet photometry has not confirmed the presence of a substantial coma or tail that would account for the observed brightness variations. If outgassing is occurring, it must be subtle, irregular, or composed of materials not easily detected at this stage. The alternative explanations venture into speculative territory. One proposal is that Atlas, like Oumuamua, might be propelled in part by solar radiation pressure, behaving more like a light sail than a rock. Could Atlas be behaving more like a craft than a comet? If so, the implication is that it possesses surfaces large and thin enough to catch photons, something difficult to reconcile with a naturally fractured cometary body. The stakes of this energy debate are high. If the acceleration proves natural, then astronomers are confronting a physics problem that challenges our understanding of cometary behavior. If it proves engineered, then the implications shift dramatically, raising the possibility that Atlas is not merely passing through but is an artifact, an object designed for travel between the stars. With anomalies still unresolved, speculation turns to purpose. If Atlas is natural, then it is a rare fragment of interstellar debris. If it is not, then questions arise about what role such an object might serve. Three hypotheses dominate the discussion. The first is the reconnaissance probe concept. In this view, Atlas could be a surveyor, designed to pass silently through planetary systems and record environmental data. The repeating light curve might then reflect rotation designed to sweep sensors or antennas across the surrounding space. The second is the seed courier hypothesis, modeled after theoretical von Neumann machines. In this scenario, Atlas would carry material or information capable of replication. The idea is speculative and well outside scientific consensus, yet it captures attention because such objects could spread slowly, yet efficiently across the galaxy. The third is the derelict theory. Here, Atlas is seen not as active, but as a fragment, perhaps once engineered, but now drifting as a relic of an older mission. If this were the case, its anomalies would be the degraded remnants of a technology that has long since ceased to function. Meanwhile, a growing number of amateur radio operators are scanning for narrowband signals near Atlas's coordinates. To date, no confirmed detections have been reported. NASA has publicly stated that it is not actively monitoring for transmissions, yet a document circulated among independent researchers suggests that internal requests have been filed for deep space telemetry allocations, a move that implies at least a quiet interest in listening. The result is an atmosphere of uncertainty. If signals exist, they are either exceedingly faint or deliberately withheld. As Atlas gains attention, institutions appear more guarded than they were with past interstellar objects. Inquiries under the Freedom of Information Act have been denied, with agencies citing reasons of space, situational awareness, and operational security. Such language is unusual in the context of an astronomical body. Observers note that NASA's communication style has shifted compared to the coverage of Oumuamua and Borisov. Press releases are sparse, and scheduled briefings have been postponed. The European Space Agency and the Japanese Aerospace Exploration Agency have also remained relatively quiet. This silence contrasts with the more open data sharing seen in 2017 and 2019, when both interstellar visitors were quickly placed under intense public scrutiny. Some interpret this as an ordinary caution in the face of incomplete data, arguing that premature announcements could lead to confusion or sensationalism. Others, however, see the possibility of coordinated silence, suggesting that agencies may be withholding information that could alter the interpretation of Atlas. Whether this reflects prudence or deliberate management is not yet known. The effect, however, is clear. The lack of transparency fuels speculation. But what exactly do they know, and why now? The deeper question remains unresolved. Is public knowledge being carefully curated, or is there simply nothing yet to report? For the public, the story of Atlas is not limited to classified memos or institutional debates. The object is real, and it can be observed. In the weeks leading up to its perihelion, Atlas should be visible through mid-sized telescopes in dark skies, its magnitude bright enough to register as more than a faint dot. Amateur astronomers are encouraged to document its motion carefully, particularly during the weeks when professional observatories face blackout gaps. Citizen scientists play a crucial role here. During Oumuamua's passage, ground observers provided critical data that later became central to the debate over its acceleration. In the case of Atlas, distributed observations could bridge the gaps when large facilities are blind to the object's position. Coordinated reports can help refine its trajectory and confirm whether its brightness variations follow a true periodic cycle. Stepping back, the stakes of this discovery are vast. In only 8 years, humanity has detected 3 visitors from interstellar space, shattering older statistical expectations. Atlas has already presented irregular photometric behavior, raised questions about possible acceleration, and drawn cautious yet conspicuous silence from space agencies. Alongside these facts stand unverified reports of radio monitoring and hypotheses that range from reconnaissance probe to derelict fragment. The recap leaves us with a choice. Either these objects represent a natural clustering now revealed by improved technology, or they are evidence of something designed. If the latter, then the implications extend beyond science into the future of civilization itself. The unresolved question lingers. Is 3I Atlas merely a cosmic coincidence, or could it be a message in motion from beyond the stars?